So last time we finally proved this equivalence of categories statement. So we proved that if we have a category of say U theta modules and the category of let's say coherent D lambda modules and flag variety. So we have functor global sections and a localization functor. So if one is anti-dominant and regular, so this is the equivalence of categories.
I should have asked long ago. QC for me, you mean
Quasi-coherent.
but as an equivalent or as a
It doesn't make any difference because the lambda is quasi-coherent in its own.
so this is not necessarily part of the generated.
No, no. So this is exactly what I will start discussing today. Yeah, just you'll see in a second. So of course, this is related to Geordie's comment. In general, we have a nice abstract equivalence of categories. We do not know anything about both sides, so we get nothing out of this. So basically, we have to restrict these conditions, and this is what, because the idea is that we say something about this by using some information on this side, and the idea is, as you will see today, to use solenonicity. So to the restricted D-model on the D-models on the other side, but then of course we have to get some interesting subcategory of this, which will correspond to polynomials. Please, that one. So this is what we are going to discuss in a moment. So first, we say that the lambda module V is coherent if locally we have that, say, any point has a neighborhood U, open neighborhood U, such that we can write V restricted to U as D lambda restricted to U, say, to Pth power, and then we have the lambda restricted to U to the Pth power. So if we have such presentation of the restricted to U. So this is coherent as D module, as I think Geordie discussed. If we assume that D module is OX coherent, then it's locally free of finite rank, so it's a connection. So this is a very special case and not really interesting on this level.
Just a trivial comment is that you only need first the subject in the middle, yes, because C is locally coherent.
Yeah.
Including the other projections of the sum of the three finite theory.
Okay. So for example, since from the local structure of differential operators, I mean, if you assume that I and Q, so these are infinite sums. See, this, from the local structure of differential operators, you know that they are quasi-coherent as all modules. From this follows that these that V is quasi-coherent as O module, if it's quasi-coherent as B. So with this definition, if I take a finitely generated B module, U of theta module, V is finitely theta module, then we can write it, and we can write this, that sequence P and U theta with some Q, and then the tensor the d lambda, so we apply localization factor. To this, and we get an exact sequence which tell us that if V is finitely generated, then the localization of V is coherent. I mean, we can say even more, because if I write down the resolution of V and apply, okay, I mean, apply delta lambda, then I will get that all derived localizations also. So this holds also for won't be relevant today, but soon. So now let's see what we can deduce from this. So assume that lambda is antagonal and irregular. I mean, for this, I could say that for this calculation I was doing, this was completely general, but now I'm going to this setting, so we're in the setting of equivalence of categories, and so let's assume that V is coherent, the lambda G, and then I can look at its global sections and consider a sequence, increasing sequence of finitely generated U theta submodules. Then we localize them. And what do we get? We get an increasing sequence of coherent the lambda submodules. So this sequence, by the equivalence of categories, this sequence has to stabilize. So the conclusion is that by equivalence of categories, that this sequence stabilizes, and this proves that V is also finitely generated because everything is net there. So the conclusion is that global sections of coherent D lambda module under these conditions of anti-dominance regularity, so using equivalence of categories, this is finitely generated. So in the situation you're in, I can just assume that we have here finitely generated, and here we replace this with coherent. But I want to extend this to other situations when we drop this. But definitely I want to drop this so that we can treat all U theta modules using this remark. So this is based on a trick we used in the proof of equivalence of categories, and also in Chris used it in the proof of Borel-Weyl bot. So the idea was to use the tensor regarding. So this is one thing they're going to explain. So what do we know? We know that if we localize finitely generated U theta module, that we always derive localizations. So in particular, localization in the situation when lambda is anti-dominant is coherent, but we do not know what happens with cohomologies if V is coherent. We would like to know that cohomologies of coherent D lambda modules are finitely generated. So this is the goal of our discussion. So this is based on the following lemma. So let V be finitely generated which the G module and F a finite dimensional then the tensor or C with F is finitely generated. So, since we assume that it is finitely generated, we can choose U finite dimensional subspace such that V is generated by U. And now the claim is that U tensor over C with F, sorry, generates V tensor F. So this is to prove this claim. Let's denote by W the submodule generated by U tensor. And let V prime is the set of all vectors V in V such that V tensor with F is in W for all F in F. Then clearly V prime is a subspace of V. Also, V prime contains U. And if we prove that V prime is G invariant, then this would imply that V prime is equal to V, and this would complete the proof because W will be equal to V tensor with F. So let's check this. This is straightforward. If we take C in G, so we can look at the action of the element C on the vector V tensor with F, where V is in V prime and F is in F. Then, by definition of the tensor product, this is C in V tensor with F plus V tensor C F. Since, first of all, since W is so our V is in V prime. So V tensor F is in W. So this is in W. First observation. The second observation is, since V is in V prime, this guy is also in W. So this implies that this thing is in W, and this proves that that C V for it's in W for any other. So C V prime, and this implies that V prime is G invariant, and therefore, since V is generated by U and U is V prime, this implies that V prime is equal to V, and V of that. Okay, so this is an important remark, and I want to point out because this is related to this story, in some sense, is that in general, analogous statements kind of sounds appealing in the first glance is false. If V is irreducible, this product doesn't have to be a finite length. And it's I think the first example was found with Stafford, and it proves that there are, I mean, one of the consequences, as you will see, of this result is that there are irreducible modules which are not polynomials. Because there was a rumor which was spread around for years that as a Barenthal conjecture, irreducibility implies one missing, but this is far from being true.
The Dragan, in fact, it's an only
Yeah.
So the statement is, it's if and only if, in fact. And we find out there,
let's see, what would, if an, yeah. That is high dimensional,
no, I mean that, like, you can check, if you can prove that B has is finitely generated, then, sorry, then B is also finitely generated.
That is high.
Yeah.
Yeah.
Maybe also time we can discuss the best, like very briefly, the best proof, like, because it's kind of some a simple argument, but there's many non-homological.
Yes, I mean.
Because this fits very nicely with our discussion last week.
Oh, okay, I mean. You are more than welcome to do this. I forgot about the details about this. I know that Stafford's paper I found totally incomprehensible.
Yes, so the bench looks like, so maybe I can explain that in the breaks, but there's a very good simple argument.
Oh, great. Oh, this would be great. Yeah, sure. But I mean, this was just a comment that although this proof is completely trivial, that in a way one has to be careful because it's very easy to slip and assume something is false. Because it looks like a small extension. Okay, so why this proves our statement? Remember, so this is an exercise. Since I use this argument and Chris used the argument, so don't want to do it again. Remember what was the idea of our proof of equivalence of categories. We were considering, in general, say, if we have a picture like this, so we have some singular weight, and then we subtract a dominant weight, and we end up in negative chamber, then we tensor with some finite dimensional representation, and we get these tensor product, which we filter and then grade, and we get just twists of this D module by all possible, say, weights of this finite dimensional representation, and then we took the say component corresponding to particular generalized infinitesimal character. We use Dragan decomposition at the action of center for such lambda, then as a so that this tensor product, which is actually U-naught module. It's not a D module split as a module of Z of G's. And this allowed us to first to push from a generic point in anti-dominant chamber to one of the walls. And if this guy is finitely generated, then the conclusion is the tensor product is finitely generated. The component corresponding to certain infinitesimal character is finitely generated, and then we get finite generation here. And of course, going from a D module at this point to the D module at this point is tensoring by a line bundle. And since coherent is a local property, then this thing stays coherent. So what we do, I mean, this is just a sketch. You go from here by geometric twist here, and coherent D module stays coherent. Then you take global sections, and these global sections are finitely generated because of the first part of the argument. Since we are in anti-dominant and regular situation, then we tensor and take this component and go back. And because of this lemma, finite generation is preserved. So this is first exercise to fill in the details. The other one is to modify this argument to cross the walls. So if I take, say, a wall and I tensor, say, I take something in the wall and I tensor with some finite dimensional representation. So you should look at Chris's lecture. Then when I take infinite, so here this blue point you should consider as a point in the wall. And I tensor with finite dimensional representation. And then I take infinitesimal character, which if you remember from Chris's talk, you should get a short exact sequence, which involves these two guys on one side of the wall and on the other side of the wall. And then the middle term is some component of the tensor product. And again, by applying a long exact sequence of cohomologies to this short exact sequence in this lemma, you can show from knowing that this guy is finitely generated and this guy is finitely generated. You can conclude that cohomologies of this guy are also finitely generated. So the final conclusion of this exercise is that if I have a coherent D lambda module in arbitrary position, then cohomologies are finitely generated. So in particular, in an anti-dominant situation, global sections go to finitely generated, from coherent to finitely generated, and localizations go also from finitely generated to coherent. Okay, any questions? So why do we want this? Because as Geordie was discussing in discussion of holonomic modules, if I have finitely, if I have coherent D lambda modules, then I can consider good filtration, so then and define characteristic variety, and we can discuss on this. But the question is, what do we put here on this side? So I will discuss the Harishchandra models now. I thought it was not so bad. I think one should get something like Linda said. I bring this from home. And okay, so you think that this is the only one I think it didn't try. Okay, this one seems to be better. I mean, this one is nice because it's magnetic, but it seems that that's not the way it's so out.
Just to understand, so you showed what we've proven just now is that for any lambda, the coherent lambda the radical side.
Yes. So
You prove first for anti-dominant regular and then you use the
yeah, so I mean, I didn't discuss this, but say if you look at derived category settings, so you drop the assumption of anti-dominance and regularities, so you can look at the derived category of your theta modules and the right category of the lambda modules, and then you have adjoint pair derived global sections and derived localization, and there, I mean, derived global sections go from complexes with bounded complexes with finitely generated cohomology to bounded complexes with coherent cohomology, and also, I mean, if theta is regular, because U theta has infinite cohomological dimension, that theta is single. But of course, for gamma, you go from bounded complexes with coherent cohomology to bounded complexes with finite generated. So yeah, so Harishchandra modules are the objects actually the over. Okay, let's see. Maybe I can take it out. Let's see. I don't think I use green. Oh, green is still good. Is this better? Okay. So again, if you think just about the situation we discussed in Borel-Weil theorem, there we have on one side, we have finite dimensional representations, say irreducible finite dimensional representations. On the other side, we have line one. And line bundles are definitely polynomial. So we want to have something close to finite dimensional, but not finite dimensional. If you think about this, then the idea is that you will have to have a module, which is not just a module over enveloping algebra, but module for some group, which is, say, smaller than G itself. So this is the setup. The G is again simple. The algebra and K is the connected algebraic group. I mean, connectedness is not important, but it will simplify some statements and they come with a morphism P of K into inner automorphisms of the Lie algebra G. And this phi is such that its differential is a map of Lie algebra of K, which I know German K, into G is, so the assumption is that this is injected. So basically, I can view K as a Lie subalgebra. Of G. I mean, you can think of it like G corresponds to some algebraic group, say simple connected algebraic group G, and K is its subgroup, but we do not need this restriction, and say definitely in the case of Alexander and Arms, you want to have this slightly more general construct situation. So if you have such a pair, I will then you can consider GK modules. So there are first pure G modules. So secondly, there are algebraic representations of K. So this means that, say, this V is a union of some family UI of finite dimensional K invariant subspaces such that the action of K on UI is given by the morphism of K in GL of UI. And the third condition is compatibility. So this, if we look at Lie algebra K, it sits in G. So we have a condition that the Lie algebra K acts first through one, and then also it K acts by differentiation of this algebraic representation, and the compatibility means that these two actions are the same. So I think the only, I will give you two examples at the moment. The only remark I want to make in the moment that here, I mean, if I draw connectedness, then I still want that K goes into G because I wanted the action of K on the center of the enveloping algebra of G is trivial. Otherwise, I get in problems. So these are our objects. And we say that GK is a Harishchandra pair if K, I mean, the group K act on int of J, int of G acts on Plagerite, so K acts on Plagerite. So the condition is if K acts on X with finitely many orbits. Okay, so let me give you some examples. First, fixable LB and N is the commutator of B itself. And N is the unipotent subgroup corresponding to N. Then, I mean, GK modules, I mean, if they're, I mean, I need somebody to correspond to highest rate modules. I mean, this finiteness is of course Bruha's lemma. And so this is Harishchandra pair. And this will correspond to highest rate category. And the other example is if, say, G naught is a connected real semi-simple Lie group. K naught is this finite center. And K, it's complexification. So this corresponds to classical theory of Harishchandra. So I would say that this category of Harishchandra modules is category of GK modules with finiteness conditions. First, they're finitely generated over G. And second is that there's ZG finite. So this means that for any V is V, V of G, V is finite dimension. Yeah.
And the second example, who is little g and who is big K? Who is the
Little G. G naught is connected real Simpson Pauli group, and G is complexified Lie algebra of G naught.
you said K is like, or you take the compact, the maximum compact subgroup, and then
K naught, let's see. I didn't.
I think
K naught is I didn't write. Is it the maximal?
And then you take
I added finite center and I erased this maximal compact subgroup. We go from K naught to complexification to just stay in algebraic.
This is like
category.
an algebraic.
Yes. Yeah. So of course, in this case, one has to prove that there are finitely many orbits, but we are going to do this next time probably, and this also follows from Ruha's lemma. And so the condition one implies that there is a finite dimensional subspace which generates our Harishchandra module, because vector says ZG finite, I can assume that this finite dimensional subspace is also ZG invariant. So I can find, say, characteristic polynomial of the action of the center, and it annihilates our module completely. And therefore, our module splits. We have like a Dragan decomposition of the module with respect to the center, and we can reduce studying the module to studying corresponding with theta module. So this is the motivation of this definition. And let's see. So this is Is this time for break? Yeah, okay, let me just say one sentence that under these conditions, we shall see that localization, first of all, because as I just said, the study of Archandra modules reduces to the study of modules in the category of, say, n finitely generated u theta k, which is just when UG action factors through u theta. So assuming that this is a theta module eliminates the need for the condition 2. So this category can be localized. So when we apply delta lambda, then we will land in the holonomic modules. And then we get some results. For example, the first result we get that these Archandra modules are finite. Okay, so this is a good place to solve. Any questions?
You don't think any, the kind of thing category reports a finite.
Oh, there's this admissibility. Admissibility is a consequence. Yeah. So admissibility was a red herring in Archandra's approach because he was starting with the group. So I mean, he was interested in group representations of Archandra models for just the two. So to get it, so he was interested to get from a group representation. If you have a group representation, say in Hilbert space or Banach space, then not all vectors differentiable or analytic. So you cannot define the action of the algebra. So he wanted to figure out a subspace where this makes sense. And he proved that the irreducible unitary representations have the property that they are admissible. This is what you want, that came out of this is finite. And then he proved that all k finite vectors are actually analytic. So he said, okay, you take the group representation, you take k finite vectors, they are analytic. We can differentiate the action, we get the action of Lee algebra, we get the them on. If we have say, Archandra model structure, then we can use Taylor series to reconstruct the group action on the original representation. So this was just the way how to to prove that all k finite vectors are analytic. You proved first that analytic vectors are density, and then you use this finite dimensionality to prove equality. Since at the moment you don't care about this connection with the group representations, so this doesn't appear, but this will be a consequence of the argument.
So I just wanted to briefly explain this fact that Dragan mentioned, which is that the vast majority of simple D modules are not holonomic. So somehow there's a bit of the argument that I understand, there's a bit of the argument that I've never looked at, and I'll just explain the bit that I understand. Yep. So we take Cn. So x is, actually x will be C2 and 7. We consider dx. So this is a bialgebra. Generated by x1 up to xn. E1 up to en. Subject to the relationship that we're familiar with. And now I explained good filtrations, which puts this stuff in degree 1 and this stuff in degree 0. But so one of these relations is delta I xj with delta ij. And if you stare at this, you realize that it makes sense to define a new filtration where this is a degree -1, this is a degree 1. Okay. And this filtration is called Bernstein filtration. Okay, so F0 is C, F1 is generated by x1 up to xn, d1 up to dn, etc. And notice that fi modulo fi minus 1 is homogeneous polynomials. So in x1 up to xn, psi1, psi n of degree I.
So did you degree -1, degree 1?
1.
Degree 1. They're both degree 1. Yeah, so, did you?
No, I really mean degree -1 then. Or, oh, degree 1. Yes, sorry. It's degree 1. Degree 1, yeah. Okay, so this is something that we can do in affine space, which makes total sense. However, when we try to glue this, it doesn't work. So this doesn't define a filtration in general, but it defines a filtration on the Weil algebra that's very useful if you're interested in modules over the Weil algebra. And it's called Bernstein filtration. And it's different to the filtration that we know and love. And so now this is where symbols live. For Bernstein filtration. Okay, so before in the good old days, when we took normal good filtrations, a symbol is something that's homogeneous in the psi highs corresponding to this. It can be anything in the excellent. Here we have something that's homogeneous in everything. And now, and the same thing. So we have T star Cn. And now the analog of the characteristic cycle is a C star invariant co-isotropic right. So characteristic cycle becomes this, where now C star acts both on Cn and on the cotangent space. Yep. And now the following nuts thing, this is the theorem of Bernstein-Lewis.
So generic polynomials of degree bigger than or equal to 4 in x1, x2, psi1, psi2 have no co-isotropic subbride. Okay, so I'll draw a picture. So what could this all be, possibly be, but the cotangent bundle of C2? I hope you all agree that that's the unique interpretation of this picture. And then we have some conical thing inside here. And this is co-isotropic. So now, if we consider a polynomial in here that has no co-isotropic subvarieties, and now consider the corresponding any differential operator that has that principal symbol. So if we take the characteristic cycle of this, this will be just this with multiplicity 1. And if it had a submodule, you would have some subvariety in here that would give you a co-isotropic subvariety, and these do not exist. Okay. So it's like a shocking, because I think in the introduction to the Bernstein-Lunds paper, they say, you know, for 2 decades, people suspected that that simple modules are holonomic. And then they say something like, in hindsight, it's totally like, there's no explanation for this like collective myth that everybody had. Maybe, yeah. Anyway, and I've never tried to look at the fact that, like, you know, this is the bit that I roughly understand, and I've never looked at the proof of this, but it's believable. And then they conjecture that this is, they prove it for dimension 2, and then they conjecture that it's true in dimension n, and I have no idea if that's no normal.
Yeah, I think Bernstein was a bit upset because there are several places where this was stated that Bernstein conjecture that irreducible implies holonomic. And he claimed that he never said that. This was before Williamson, so there are no documents. Yeah, so who knows? Right.
And so like on binary, just take this forward, get something that, you know, at least it won't be simple, I guess, but big word.
But you can intermediate extend it. Yeah.
Same thing. So
Yeah. And somehow this kind of also shows that, like, you know, the vast majority of this, like over the Weyl algebra, the vast majority of D modules have this codimension 1 characteristic variety. And so they're like extremely far from being holonomic. And so the vast majority are like that, and somehow holonomic is very special.
why do you say that?
Well, you know, like if I think about a ring and I try to produce a module, like the first thing I try to do is mod out by, yeah, the first thing you quotient by something, and then maybe you can quotient by something else, you know, and almost all the time when you do that first step, you can't do anything more, and it's simple. And Stafford discovered this first example where he generates a left ideal that's maximal. The single element generates a left ideal that's maximal. That was the first example. And as Dragan said, it was like this kind of massive computation no one understood. And then Bernstein and Lunds came along and said, well, actually, this is generic behavior. Yes. So it's basically the fact that, so Bernstein and Lunds do say this in the paper. Yeah, sorry, I'm blanking on what it means. It means something, and it's in the introduction to the Bernstein and Lunds paper. Yeah. So maybe I leave the punchline and erase the rest of the Dragan.
really say anything. Because, so there are some comments about this method of it I want to make, because we won't probably have time to go into these things, but I just want to point out that in a way, Bernstein filtration was, at least from the point of view of D modules, was predecessor of the standard filtration in D module theory. In Bernstein's original papers, he considered this filtration, because in this filtration, the pieces in good filtration are finite dimensional, so you can use Hilbert polynomial to measure the growth, and he defines Bernstein dimension and Bernstein dimension and multiplicity using just standard Hilbert polynomial argument, and then he observes that dimension is bounded by n. So it's dimension of the non-zero module is bigger or equal to n, and this is his definition of a norm. And the idea, and actually the original proof, which is kind of messy, is based on the following simple observation. Then in the case of one variable, this is the generating a relation of biology. So if you have a module over differential operators in variable one, this must be a representation of these commutation relations, and they cannot be finite dimensional, because this side has trace 0, so your partial x is 1. So if you take if you assume that there is a finite dimension or the realization, you take the trace, you get on one side 0 on the set dimensions. So basically, this is either 0 or 1 dimension. So there are no small modules, and so he does the induction in the proof to prove this statement about Bernstein dimension for all one. And then there is an ingenious argument kind of technique. He puts, I think, more and more weight on these variables and creates a family of filtrations, and shows that the corresponding characteristic for that is, although they're different for different filtrations, but they have the same dimension, and at the limit, he gets the statement that characteristic variety Geordie described with the dimension greater or equal to 1. So this was his proof of the statement for the Weil algebra, and then you can, using Cauchy-Lira equivalence categories, you can reduce general proof to the Weil algebra situation. So this is this approach can be generalized. Of course, the main issue is that Bernstein filtration works on here, because otherwise there is no natural filtration on regular functions. Okay.
Can so I've got so there's this gather in volatility theory,
Yeah.
and I have no idea how to place that historically.
Oh, this is later. I think Bernstein was definitely the first. Then there is a problem with Japanese school, because they all say this was done in Cauchy-Lira's thesis in Japanese. I think it was, I think now there is an English translation. I think that it's a part of the history which is very hard to figure out, because Russians do not code Japanese, do not code Russians, so it's hard to. How, and the Gagarin is definitely later known to claim priority.
It can be somehow more general. Or, why not?
I don't think so. I mean, I think Gagarin is just who is completely from different world. I think it's. Yeah, but there. I mean, there is definitely bad blood among Japanese. I mean, Kashiwara is one of the guys who claims everything, so. I mean, I don't know if Wolfgang ever told me this story about Rebecca. So Wolfgang and I figure out that everything would look normal for Vita as we expected for Vita decomposition here in Poles. And but we had no idea how to prove it. And then we were trying to figure out what were the consequences. And then Wolfgang figure out the trajectory to avoid the decision. But definitely everything was compatible with the composition theory. So Kashiwara comes to Salt Lake, and I asked him, is it possible that the composition theory holds for all homonomial? He said, no. Must be easy to find the counterexample, and then he walked around, smoked his cigarettes, and I cannot find the counterexample, and this cannot be true. So 5 years later, he announces his particular conjectures that this is true, and thanks Harry, Yao, other people, but he doesn't mention this conversation at all. So, and then, of course, now this is known as particular conjecture. And also there are issues with this L2 cohomology stuff. He did with Hawaii and Schmidt, atomic couple. So I don't know, it's probably impossible to figure out exactly what was going on. Because Bernstein, of course, was developing this to solve this Gale-Files problem of metamorphic continuation of these distributions. Anyway, you'll never figure out the details of math history. So where did you find this black pen which works so well?
I did press a lot and then it didn't work well. But then once I talked to the audience a little bit and then returned to the board, it was miraculously very good.
Oh, that's neat. Of course, the problem with black is that the ways it does it has to press it. Okay, so now we define this category and use theta. Hey, these these GK modules which are finitely generated and have infinitesimal character given by theta. And in the same fashion, we can define coherent d lambda k modules. So which first coherent the lambda modules. The K equivariant. And then OX modules. And we have a compatibility action because if we differentiate A action here, we get the action of the Lie algebra, and this action of the Lie algebra factors through on X module, and we want that it agrees with the action of Lie algebra K, which maps in U of G, and U of G maps into U theta, and this gives global sections of the lambda. So this is and basically by checking million formal details, we can show that if you localize U theta K modules, you get coherent V lambda K modules and global sections from that. So we have this argument pair of pointers, and we know we can prove that, say, if lambda, I mean, basically we prove this, if lambda is anti-dominant and regular, these two factors have equivalences of categories, and if lambda is anti-dominant, then this category is quotient of this one. So now the reason why this all works is what I mentioned at the beginning, that under this assumption we can actually prove something about the right side. So this is the critical theorem. So I will call, as a shorthand, I will call objects here Harishchandra. The theorem is that so this is the main observation. So I will prove this, but before that, let me point out some consequences. First of all, what was, as far as I remember, proved in Geordie's talk, holonomic modules are of finite length. So finite length is for the modules is basically local property. So you don't have to worry about twists. If I mean, we are going to prove next time some results about irreducibility, which imply this, that if you have a module which is of finite length on an open cover, then it's of finite length. So you don't have to worry about twists. And if you know this, then you know that objects on this side are of finite length. So if you take for any theta, you take an anti-dominant lambda, this side is a quotient category of that side. And what can happen, since the object is of finite length, that some irreducibles can be portioned out or they stay reducible. So this is another simple exercise. And with this, you conclude that all, so you have a corollary, then all objects in and u theta k are of finite length. And this implies the following corollary, as I discussed before, that all Harshchandra modules are of finite length. So in our examples, this is, as you know, this is simple for highest rate modules. I mean, that's corollary. So this was our first example of Harshchandra category. But this is a very difficult result for Harshchandra modules for semi-simple groups. And it was proved by Harshchandra, but his original proof used theory of invariant eigendistributions and all kinds of technical results to establish this. And before V modules, there was no simple transparent proof of this fact. So it's kind of amazing that this is all resolved by homogeneity and in a uniform way. Okay. So let me check. Okay, so now you can try to prove this theorem. So first, we want to show that there exists K equivariant good iteration of a Harshchandra sheet. And the idea is, I mean, this follows from some formal arguments, but it's this is too complicated. So let me give you a simple argument which uses twisting. So you take V, which is an object in and of u theta k, and we can twist it by a line bundle so that it goes to antidominant chamber. So our lambda plus mu is in a chamber when we have equivalence of categories. In this case, I know that gamma x v is a Harshchandra module. So I can take a generating subspace U such that U is finite dimensional. And K invariant. So then, when we have this, we look at, so let me denote by F of d lambda the degree filtration of this twisted sheaf of differential operators. So I define F P of V is F P of d lambda tensor over C. I is the image of this tensor, this U. So basically, I generate P piece of filtration by these finite dimensional space of global sections, and the action of these differential, twisted differential operators of order less than or equal to Pns. And then there is an exercise that Fp of V is a good filtration. So we look at, let me remind you that GR of d lambda is independent of the choice of lambda. This is just sheaf of symbols of differential operators on X. And it acts on GR of V, and GR of V is just a coherent module over the sheaf of symbols. And then the characteristic, we have to look at an annihilator of this module here and look at zero set in cotangent level. So observe that if we take C in Lie algebra of K, then this action of C actually maps, since these pieces are K, filtration are K equivariant. Yeah, so this is proving there exists a K equivariant good filtration. This is our filtration, this property. C maps Fp of V into Fp of V. And this is a differential operator. I mean, C determines a global differential operator in the first piece of filtration of d lambda. So we see that C annihilates so the sigma, let's denote by say sigma of C, so this is the symbol, annihilates GRE. On the other hand, let's see what this means. So let's look at the K orbit Q in X. And we denote by NX Q the conormal variety of this orbit. So this is set of x omega. X is in Q, and omega is a cotangent in a cotangent space of x, but orthogonal to tangent space to the orbit. So this is then x dimension. So now we use the assumption that the number of orbits is finite. This means that the union of nx cubed over, say, all orbits cubed, and put over here, this is say, let's call it nk, is closed variety of dimension s. Dimension equal to dimension of x. Now, since the symbol of C annihilates GRV, so the symbol of C is an annihilator ideal of this module. On the other hand, C, by the very construction of this, annihilates, vanishing on the union of these conormal varieties. So this implies that since the annihilator is bigger, then the ideal generated with symbols of seems that the set of 0 points of the annihilator will be a subvariety. But as Geordie explained, talking about holonomic modules, for D modules, characteristic variety has to have dimension. It's either 0 or dimension is greater than dimension of x. So since this is inside this variety and dimension is equal to dimension of x, it's just a bunch of components of this n of k. And anyway, it has to be of dimension of x if it's non-zero. So the Kirchner, this Kirchner sheet is holonomic, and we adapt. And if you think about the case of transitive action of k, then the conormal variety of the orbit is just a 0 section, and this tells us that any Harish-Chandra sheaf is a locally free OX module of finite rank, so it's a connection. And then since if it's irreducible, it's a line model, and this gives you a general nonsense proof of Borel-Weil bond, this situation. So this proves this theorem, and Now, yes, I think it's good. I just wanted to say one thing, that if we want, so what is left out? We didn't prove that in our charter case, there are finitely many orbits. I think I will do this next time. And then one thing, I don't think that George, you didn't discuss the classification of irreducible objects. So the whole point of polynomial things is that it's very easy to describe all irreducible objects, and then you can count them, and then you count irreducible objects here by applying global sections. Of course, you have no idea what these modules actually are, but at least you will see there are finite many, then and you will see how it looks like. Then you figure out what the. Okay, so